Hello everybody, welcome back. This is it, our last note of the semester, last note of chemistry. Alright, so I want to spend a little bit of time and just take up one of the questions from the mini activity that I left you with yesterday for homework. So I'm going to take up question 2A, and then I'm going to finish our last note on consumer products, consumer cells and batteries. Alright, so let's go to the mini activity. Okay, and the question says, for each of the following, sketch the galvanic cell, including the following information: cathode, anode, half reactions at each electrode, movement of electrons, movement of ions, and the balanced net ionic equation. Okay, so we're told we have two elements, magnesium and zinc. So I'm going to draw my two beakers. Magnesium and zinc. And then I have magnesium ions in here and zinc ions in here. And I have my salt bridge, and I have a wire. And typically I would put something in the middle of that wire, like maybe a bulb, so the bulb might come on. In this case, what they've done is they've used a voltmeter. So they put a voltmeter here to see how many volts that they're getting. And the question is, which way are the electrons going to flow? So I've got magnesium and zinc. Now, I may have made a mistake with this yesterday when I was doing it. So what's going to happen is I'm going to look on my activity series and try and find the one that's higher up on the list. So the one that's higher up on the list is the one that's going to give up the electrons. Right? The one that's higher on the list will give up its electrons. So in this case, for magnesium and zinc, magnesium is higher than zinc. So because the magnesium is higher than zinc, the magnesium is going to give up its electrons and electrons are traveling that way. Okay, whichever one's higher on the list is more easily oxidized and it will give up its electrons. So if electrons are leaving, that means the magnesium on this side is giving up its two electrons, and it's going to become magnesium 2+. And on the right side, the two electrons are coming in, and they're going to join the zinc ions to make zinc. So I can see right off the top here, again, first and most important question, which way the electrons are moving. Okay, so again, this one becomes the negative electrode on this side, which is the anode, negative anode. This side is positive, positive for T, cathode. Down at the bottom here, I can see that I have the GR going on here. It's my reduction. The zinc ions are gaining electrons. Here the magnesium atoms are losing electrons. Now it asks me also, which direction are ions moving? So in my salt bridge, I have positive ions and negative ions. Now notice that if electrons, I got positive and minus in here, if electrons are coming this way into this chamber, making this negative, that means the positive ions that are in the salt bridge are going to travel that way, and the negative ions that are in the salt bridge are going to travel that way. Okay, so there would be a mark on the test also. Okay, so positives going to the side where the electrons are moving. And then the last thing it asks me, so I've identified direction of electron flow, direction of ion flow, I've labeled the anode and cathode, I've written out my oxidation and reduction half cells, and lastly it says, what is my overall reaction? Well, I've got a magnesium on the left and a zinc 2+ on the left. And I'm going to turn them into a magnesium 2+ on the right and a zinc on the right. right? And notice that I had plus 2 electrons on this side as a reactant and plus 2 electrons on this side as a product, so everything balances. And there's my ionic, there's my whole cell reaction. Okay, so that's how your basically galvanic cells work. Now, I said to you yesterday that galvanic cells work a lot like batteries. And really, if we look inside a battery, what a cell is a cell contains one oxidation chamber and one reduction chamber. So if you buy your standard AA or AAA, AA or AAA or C cell or D cell, right, inside here there is one container or one section for oxidation and one section which is where the reduction is going to happen. So I have two chambers inside here, an oxidation chamber and a reduction chamber, right? And the difference between the electrons leaving the oxidation chamber, Leo, and going into the reduction chamber, Ger, is the potential or voltage that we're going to get. Now, the difference between the different types of batteries, AA, AAA, C cells, D cells, really, it's about the amount of chemicals that will be in there. All right, so again, when I put more reactant in there, the reaction will go for a longer time before it runs out. Now, if I look at something that's not 1.5 cells, like say your rectangular batteries, right, with a negative and a positive on top, right, electrons again are going to do the same thing, but what I've got inside that battery is not a simple cell. I've got a series of cells that are each going to give electrons 1.5 volts of potential. So let me just make this a bit bigger here. So if this was a 9 volt battery, so let's get rid of. Okay, what I might have inside here, separating this side and this side, oxidation and reduction, another set of cells. Now it's not going to be quite set up this way, but this basically represents 3, 4, 5, 6 cells. So electrons are going to ultimately, from here, they're going to travel up into the next cell, into the next cell, into the next cell, and they're going to continue going through each cell, gaining more potential, gaining more energy as they go through each cell. So by the time they come out of the top of this battery, right, this is actually a battery, the other one was not a battery, as it comes out of the top here, it's carrying 9 full volts of potential, and then the electrons are going to return back to the 6 chambers on this side, which is where my half cells are. So I've got 12 chambers going on in here. Each set of 2 chambers provides electrons of 2 half cells, which give me a cell, which is 1.5 volts. So the difference between a cell and a battery is a cell has only 2 chambers, right? This is multiple cells, right? This is 6 cells that are all joined together. Remember, each cell is 2 chambers, a Leo and a Ger, right? And a Leo and a Ger, and a Leo and a Ger, and a Leo and a Ger. So I've got 6 cells going on here, and each one gives electrons a little more voltage or a little more energy. So when they come out the top, they've got quite a lot of energy, right? A lot more than I would have had. I could achieve the same effect by taking 6 individual cells, 1, 'kay, and if I did that, electrons coming out of this end they would get 1.5 volts here, another 1.5, 3, 4.5, 6, 7.5, 9 volts, and they would come out of here. If I was to read the voltmeter, it would say 9 volts, and they would go back to the top to replenish the electrons that left each of those cells. All right, so a cell contains 2 half cells, and a battery is multiple cells that are set up together, right? Like that 9-volt battery there on the right. Now, we typically have 2 kinds of cells that we use. We have wet cells and dry cells. In a wet cell, it is exactly what we would expect. Like the beakers we had a minute ago, I've got a liquid in both of the chambers, right? In a dry cell isn't totally dry because my compounds still need to be dissociated. My ions need to be dissociated, but instead of having a lot of water in there, it's very, very concentrated to a point where it's actually more of a paste than it is a liquid. So in the wet cell, I actually have liquid solutions, and in the dry cells, like the batteries, the cells that we normally have, most of what's inside here is a paste. So if one of these fell and broke open, right, or started to leak, you're not going to have a big puddle of liquid that comes out of this because most of it's drier. It's drier than toothpaste, and it's almost powdery, but it's like a moist powder. It's like damp soil. Okay. And then I'm going to have my negative terminal at the bottom here, and my positive terminal at the top. And electrons are going to come out of here, go to there, right? And I'm going to have my 2 reactions, my anode and my cathode. The anode here, which is where the negative electrons are coming from. The cathode is this material on the outside here, which is collecting the electrons. That's working as my positive electrode and collecting my electrons coming from the other end. And then notice that there is this kind of sleeve that separates the one chamber from the other chamber. Right? And what happens is I can have oxidation going on here, and instead of electrons just going to the reduction material, they can't get there, so they've actually got to travel around through the circuit. Now, most of the batteries that we would typically have used historically, if you go to the hardware store and buy batteries, or drugstore for batteries, or the dollar store for batteries, a lot of them are alkaline batteries. Alkaline means base, right? In terms of acid-base chemistry, alkaline means base. So the pH was quite basic, pH 13. And again, what that means to you is it's quite corrosive. So if a battery actually split, or sometimes you'll see at the bottom of a battery, it's actually an old battery, and they've got all this white stuff that builds up on the bottom of the battery. What's happened is the seal has gone there, and some of that alkaline material has come out. But again, notice you don't want that stuff touching your clothes or your hands, right? So you think, I thought it was acid in a battery. Well, these are alkaline batteries. And the reason why they're alkaline is it facilitates the transfer of electrons from one to the next. From the reduction chamber back to the oxidation chamber. Now, if we look at what that separator is between the oxidation and the reduction, it's a membrane, right? It's a kind of like a cell membrane. It's a membrane that allows some things through, but not other things through. So in the cathode half reaction, I see that manganese dioxide here is going to turn into dimanganese trioxide. If I look at the oxidation numbers here, oxygen is -2, manganese is +4, and on this side, oxygen is -2. There are 3 -2s, so the manganeses are actually +3. minus 2 and plus 3, and here I've got plus 4 and minus 2. So notice that the manganese is going from plus 4 to plus 3. How do I do that? I got to lose some positive charge, or I do that by gaining electrons. But there are 2 manganeses, so I'm going to need 2 electrons here to make the transition. In the so that is my GER reaction. That's my reduction reaction. In my oxidation reaction, zinc, which is 0, is going to turn into zinc oxide. Oxygen's minus 2, zinc is plus 2. So to go from 0 to plus 2, right, I have to gain positives or lose negatives. So I'm going to lose 2 electrons over here. Oops. And that's going to be my Leo reaction, or my oxidation. So within that battery, I have the oxidation reaction going on and the reduction reaction going on. And for each of those reactions to happen, if the manganese dioxide here doesn't get electrons, it can't react. It can't turn into product. So it will sit there until it gets electrons. If the zinc and hydroxides here can't get rid of their electrons that they produce, this reaction stops too, and the zinc will sit there until, as long as I'm not using the battery, the electrons will stay here and they won't try to leave. It's only when I actually complete the circuit and allow the electrons to move from the zinc cell to the manganese cell that I actually allow the reactions to happen, which means the battery will start losing reactants, manganese dioxide and zinc, right? And until they're gone. Now notice that the reactant here with the zinc is hydroxide, and the products of manganese dioxide are hydroxide also. Remember, that's the chemical, that's the ion that we associate with bases or alkaline solutions. So that's why these are called alkaline batteries. To make these reactions happen, we make sure that there's a surplus of hydroxides in the battery to allow for this reaction to happen and continue happening until the zinc is all gone. All right, so there is how our traditional batteries work. Now, like I said earlier, as I choose which metals to use for oxidation and reduction, I can decide how much energy I'm giving the electrons or how much voltage that cell is going to have. Now lastly, we know that some cells and batteries are rechargeable, like the ones in our phones, the one in our laptop. Lots of different things use rechargeable batteries, and basically what I do is I provide an outside source of energy, right? Provide an outside source of energy to push the electrons in the opposite direction, right? And what that does is it reverses the redox reaction and generates back the reactants that I had originally. Now, today's rechargeable batteries are way more sophisticated than this, but for the most part, that's the whole premise. Now these are actually controlled by there's computer technology in our batteries now that makes sure that they're working properly and they control things, and that's what gives batteries memory. So they're more sophisticated than what I'm saying here, but that's the basic premise. So we call batteries that cannot be recharged primary cells. Cannot be recharged, and those that can be recharged are called secondary cells. Probably the most common one today would be the lithium ion cell, and that's the one that we use in most of our computer devices and electronic devices that are rechargeable. Alright, so 10.5 here talks about the use of fuel cells. And a fuel cell works a lot like a galvanic cell, except it's a couple of big differences here. So I'm going to switch there's a picture here of a fuel cell, and what I can see is the reactants for this fuel cell are hydrogen gas and oxygen gas. And as the H2 reacts with the O2, it's going to form H2O. Now, this reaction works very, very well under high temperature. This potassium hydroxide solution that we're using is over 100 degrees Celsius. It's actually closer to 200 degrees Celsius. And because it's so hot, as the H2 and the O2 come together very easily, they turn into H2O. The O becomes O2 minus by gaining electrons, Gr, and the H2 becomes H plus ions, which can join with the O to make H2O, with a 1 plus oxidation charge. And in doing so, as the H2 becomes H plus, it loses an electron, which can be used to run any circuit. And then they'll go back to the O on this side, to O2s to become O2 minuses, and then they will connect with the H plus to turn into steam, and then there's usually a way for the steam to exit from the system. So long as I keep filling this thing up, this thing will run forever. Now, one of the big differences between this cell and the other cell that we just looked at in terms of a galvanic cell is that it's not closed. It needs to be open to allow us to add more reactants and to allow for the product to escape. The other thing that we do differently here is we use electrodes that aren't going to get bigger or smaller. So we usually use inert electrodes, which would be either a chunk of carbon or else a platinum electrode. A lot of these things use platinum electrodes. They're very efficient. They're excellent conductors. And what happens is they'll allow for the electrons to flow, for the reaction to happen, but they won't dissolve or grow. Okay, so there's the main advantage of this type of setup. Now, ultimately, if I've got a way of making electricity, and I say, okay, what is the waste product from this type of technology? Oh, it's water. Well, that's amazing. I mean, what can we think of? Think about a car, think about anything that uses even batteries. The waste that they produce is not H2O. I mean, H2O is essential for life. It's the most important molecule on the planet. If it's the waste product of our cell, of our fuel cell, that's terrific. Why doesn't everything do this? Because basically, this is very expensive to make, right? To make hydrogen gas costs a lot of money, and the technologies that we use for making hydrogen gas are not terrifically, they're not easy to use. Okay? The other disadvantage to this is explosive, right? It's highly, highly flammable, and you don't want to have this inside a car or anywhere else where a collision could cause this thing to be ruptured, and you'd have a big, big problem. So fuel cells are a possibility, and there's lots of potential for fuel cells, but we're certainly not there today, and I think we'll have better answers than using fuel cells before all is said and done. Okay, so just to wrap up then, so we finished chapter 10 today. I'm going to leave you with some questions on page 360 here, which are about today's note, and I'm going to leave you with the chapter 10 review, which is right here. Not all the questions, 1 to 17, 28 to 30, 34, and 37. So Wednesday this week, so today is Tuesday, Wednesday this week, tomorrow we will have the review. Thursday I'm going to have a review class like I did on Friday for the Chapter 9 review. If you have not seen the Chapter 9 review from Friday, I highly, highly encourage you to go and spend the hour to watch that live stream video, that Microsoft Stream video. Again, I'll put a link for that in the announcements, and you really want to go ahead and watch that. It will give you a lot of just kind of pointers in terms of how electrochemistry works. Our tests for this week will be on Friday, and that will be